Good morning. In previous lecture, we've seen how alkenes can be prepared from several different classes of compounds. And today we will see the reaction that alkenes themselves undergo. And as you will notice, alkenes are quite reactive compounds and can give rise to a number of different classes of compounds. So we'll spend most of today's and next week's lecture talking about the reactivity of alkenes. The center of alkene reactivity lies in its pi bond. So as we know, in the double bond that connects two carbons, one of these bonds is sigma bond and the other one is pi bond. And sigma bond is stronger than pi bond. So what can often happen is that fragments of type AB can add itself across the pi bond, replacing that pi bond with two sigma bonds, and since they tend to be stronger, this leads to a release of energy, so this is a favorable reaction. So basically we have a pi bond transforming into sigma bonds. The simplest example of this reaction we've already been introduced to, and this is just hydrogenation. Of this molecule. And these reactions in general are known as addition reactions. And they can often be viewed as the reverse of elimination reactions, because elimination reactions tend to form the double bond, while addition reactions tend to destroy the double bond and form sigma bonds. So one can write this formal scheme which has CC plus AB in this direction proceeding as addition, while in this direction proceeds elimination, to give us the system we already saw. Okay. Of course, the third big class of reactions that we've already seen are substitutions, which basically do not change things much except that they replace one functional group with another. But when we talk about additions onto alkenes, it's important to realize that not anything can add to alkenes. So the AB fragment has to satisfy certain requirements. And if we, to understand those requirements, we should look at the orbital picture of alkenes yet again. And what we see when we look at this is that the center of alkene reactivity lies in this pi bond. In the pi bond, which is electron-rich. And in order for something to react with the pi bond, we need that species to be electron-poor, which means it needs to be an electrophile. And hence, the vast majority of additions onto alkenes are known as electrophilic additions, and they proceed, you might want to write that, electrophilic additions. And they proceed through a sequence of steps. The first step is typically, if you wish, a nucleophilic attack with this double bond to the electrophile, which then leaves one carbon in the double bond in the form of double bond cationic, and the rest is now electrophilic. So if we start with an alkene here, have it react with an electrophile. The first product would be a carbocation. And this carbocation can react in a fashion that we've already seen in SN1 reaction, where we have a nucleophile attack the carbocation, some sort. And of course now we don't need a very strong nucleophile since we have a carbocationic species which is very reactive, to get finally addition product. And we see again that this carbocation is a junction, a crossroads for many different mechanisms. It occurs in electrophilic addition onto alkenes, it occurs into SN1 reactions, it occurs in the reverse reaction from the electrophilic addition, which would be the E1 reaction, and so on. To illustrate this in an example, we will, and this is an example we will already talk about more in a little while. The simplest electrophile is just a proton, and so we can have an alkene attack this proton to give us cationic center here and pH bond here, and then this can react with the bromide as a nucleophile, and this is nothing else but the addition of HBr to give us a brominated alkene. Now in the next subtopic we will see the details of these additions of hydrogen halides onto double-double bonds.